Hi, everyone. Thanks for joining our session. We're going to be talking about improving power grid reliability using IoT analytics. And my name is Jim Brown. I'm Director of Data Science at Neudesic.
Hi, everyone. I'm Mingjie Yu. I'm a Senior Data Scientist from DTE Energy under the distribution operations.
Thank you, Mingjie. So if you're like me, you kind of take grid reliability for granted. I mean, just about every time I go to use power, it's always there. I turn the lights on, they come on. Every time I use my computer or charge something, I always have power. But recently, a few months ago, during the COVID lockdown, I lost power for pretty much the entire day. And I quickly realized how much of our modern lives come to a close as soon as you don't have that power. I couldn't make coffee in the morning. I couldn't use my microwave. I couldn't use my electric stove. It was like everywhere I went, nothing was ready to go. All I had left was my cell phone and had about 20% of power, and I just had my iPad and whatever other battery I had. But so it really was about just losing the conveniences. But if you live in Texas, you have a much different story with grid reliability. It actually, during this last winter, it was such a bad winter that many people went without power for a long period of time, and it actually became deadly in many circumstances. And so that points out that not only do we, as people and consumers, depend on grid reliability, we also very much depend on strong utility companies that deliver us that power. And so that's why I'm so proud to be working with DTE on such an important problem. And here's what we're going to be talking about today. We're going to spend just a few more minutes on company introductions, and then we'll go over the business challenges. And this is what DTE was facing. And then we'll work on describing the solution architecture that we developed, and then we'll do a demonstration. So just a little bit more about Neudesic. We are a services consulting firm, and our mission is to help our clients land on the winning side of digital transformation. So we've been around for about 20 years, and about 10 years we've been doing utilities consulting, and we have a utilities vertical. And DTE is one of our primary business partners and customers, and we have quite a few other utilities that we work with as well. So we have quite a number of technical offerings, ranging from data and AI all the way through hyper automation and many different types of solutions. So we use our data and AI platform accelerator, which helps companies get onto Databricks and the Delta Lake and being able to quickly get that started and to be able to build models and solve your business problems. So next, Mingjie is going to talk about DTE.
Yeah. Okay. How about this? Okay. Thanks, Jim. So first, let me briefly introduce DTE Energy to you. So DTE Energy is a Detroit-based energy company. For DTE Electric, we have the electric generation and distribution, serving about 2.2 million customers in southeastern Michigan with a system capacity of 11,084 megawatts. So it is the largest electric utility in Michigan and also one of the largest in the nation. In terms of DTE gas, it is engaged in the storage, transmission, distribution of natural gas. So we have about 90,000 miles of distribution and serve about 1.2 million customers in Michigan. DTE also includes the non-utility energy business which focus on natural gas pipelines, gathering and storage, and also power and industrial projects, as well as energy marketing and trading. So you can see a picture of Michigan here. Our service territory is about 7,600 square miles. So the aspiration of our DTE is to be the best operated energy company in North America. So every department, every division of us focus on that. For us distribution operation, we want to provide our customers with a more reliable and a safer power future. Now, this is basically about our project we implement. So the main business challenge we faced is that the current strategy depends more on the historical information at a high level of system, and mostly consider the long duration outages only, and it depends on the expertise of our engineers to know where's the problem, what to do, and how to manage this. So the key aspect of our project is try to combine a lot of holistic information and advanced analytics. Then we can identify those small areas that experience poor reliability, and we define them as hotspots. Then we can empower our engineers with a lot of information that are more timely and specific about the things they can do right now. So this is an example of two major reliability actions that we need to decide. Since the fallen trees are responsible for nearly 70% of outages, and we have a lot of tree trim crews go out to maintain those trees. And this is a huge investment for our DTE. So we have to decide where we should send those crews and what they should focus on. And another main cause of the service quality issue is the aging equipment. So our engineers also have to decide which equipment is coming to the end of life and what part of it needs to be replaced or just reinforced. So when the outage happened, for now, we have to rely on our engineers' expertise to decide what action they should take to resolve the issue. And this is really a big challenge and something really difficult for them to do. And we think a lot of this is really a data problem. So one of our model's purpose is to identify the cause of those reliability issue. Is that due to tree or just due to aging equipment? Then we can give our engineers a good suggestion on what and where is the problem. And they will know what resources are needed to solve this problem. So the first data source available to our project is from the AMI meters. We have about 2.6 million AMI electric meters across our system, and we got tons of data from these smart meters every day, including the usage and the service quality data. So those AMI meters report the usage data every 15 minutes for the polyphase meter and hourly usage for those single-phase meters. In the meantime, they also report the service quality data, like the outage information, when the outage starts, when it ends. And they also keep track of all the outage and voltage alarms in real time. And also they will record all the voltage, when the voltage move beyond or below some certain threshold. And we also get the actual voltage readings for each 5 minutes from those AMI meters. So there are millions of data points from these smart meters streaming into our system every day. So we also have another set of information about how our equipment are connected together in a distribution network. So we use the network X to develop this connectivity graph instead of our solution. Since we want to search for the hotspots on this connectivity graph, instead of just focus on their geographic distance. So the left graph here shows the electric system. The electricity is generated from the power plant, then transmitted through the subtransmission system, then goes to the distribution system. So our project's focus is in the distribution. We have the equipment chain from the subtransmission to substation, and then goes to the circuit. And from the circuit to transformer, there are a very number of devices between them, such as fuse, switch, recruiter. Then transformers is connected to meters, and the meter is the lowest level of the system. So the right graph shows an example of the connectivity graph. So you can see for this one subtransmission, it is connected to 3 substations, and then they connect to several circuits. And between the circuits and the transformers, there are a lot of another devices. And all the meters are attached to their transformers. So the distance between 2 meters in our project is defined as the number of hops between them on this connectivity graph. So for example, if you look at the bottom line, the last 2 meters are next to each other from the geographic perspective, but they are actually come from different substations. So they probably have a very different power quality behaviors. So they are actually far away from each other in terms of the equipment system. So this graph will help us to better understand where is the problem and what is the suspected equipment with the issue. So as you can see, we got a huge amount of information every day, and all of that together makes finding insights so difficult. So we can look many different places. We could analyze different pieces of data and in many different ways. But how do we make this analysis useful so they can help our engineers to better understand what it is? So Jim will talk more about our solution architecture for this question.
Okay, here's our solution architecture. And this is simplified to just let the main points come out. And on the left, we start with the AMI meters. Those are the smart meters that Minji talked about. And they're reporting those 3 different types of events. So we have information on the outages, their usage, and also low, high voltage events as those occur. So those are transmitted wirelessly over a mesh network. And that's all part of the AMI infrastructure. And that all gets brought together and then ready for ingestion by this whole AMI infrastructure piece. And so that goes into Azure Event Hubs and then gets streamed into, using Spark Streaming, into a landing area, which is a Delta table that has all of that information inside of it. And so we have several Azure Databricks notebooks that go over that data and then summarize it and enrich that information so that we can use that to detect the hotspots and also the suspect devices. And so an important piece of information is that OMS, that's the outage management system. And what that is when there's an outage that occurs and DTE sends a crew out there, the crew actually records what they replaced and what the cause of that was. So if a tree had fallen over on a line, they would report that as the issue that happened. If, for example, it was an equipment failure, they would report that and what device they actually worked on. So all of that information gets put into what we call the AMI summary information. And that contains quite a number of notebooks and summarization techniques to get it ready for further analysis. And so then across the top there, you see the section of hotspot creation. And this is where we take that AMI summary information and then we do outlier detection on it. And we do a simple process using Mahalanobis distance, and I'll show you that inside of our demonstration when we start to look at this more. And so what we do is we take those 2.6 million meters and we take away the ones that are experiencing relatively normal reliability, and we focus only on the extreme outliers. And so that ends up going into another delta table of just poor reliability meters, and that's typically around 60,000 is what we're finding right now. So we combine that with that equipment chain, that device chain that Minji was talking about as well. And that's where we use that distance matrix to go into DBSCAN. And that clusters these based on their network hops into groupings of hotspots. So that's one of the primary outputs of this are these hotspots that are being generated. Another path that we do is we take that device chain and we try to figure out what sort of AMI events, what is the source, where is that actually coming from? And so this is something that we're experimenting with, and we think this is going to be a really good contribution to the industry, and being able to take over a 24-hour period all of these different momentary outages, voltage events, and taking a look at which devices are playing a role in a high percentage of those. So in a typical day, as we've been looking at this, we see that there are just a handful of devices that are pretty much involved in just about every one of them. So this gives DTE the opportunity to have someone check this out and go and work on this potentially before failures are occurring. So it may be an early warning that something is going to happen in the network. And so we're really excited about that. So here I'll flip over to the demonstration. I'll show you how we create the hotspots. So now we're looking at a notebook that is basically going through the hotspot clustering piece. And so we pick up after the meters have already been put through the outlier detection. So the way that works is we first do some aggregations and basically score each meter along the voltage events, and at different time intervals we take these as well. How many sustained outages have happened, and also momentary outages as well. So all of that together gets computed with Mahalanobis distance, and then we use a chi-square cutoff to be able to determine which ones are experiencing unusually poor reliability. So we experimented with quite a few different techniques on what would be the best way to make this happen. And a big part of what I always do is I try to use the simplest method whenever possible. And this one turned out to be, even though it is a simple multivariate technique, it turned out to be a very good way to find these. We tried isolation forests. They had just about the same sort of results, but this was a bit more explainable. So that's why we selected that. So sometimes you'll see that we use things for simplicity and to make this process a lot easier as we move through this. So here in Command 4, we're just loading the device chain. So we pickle this off so that it's easy to be able to load it back in and be able to use it in various notebooks. So the next piece here, what this does, and I'm not going to show the code because it's just lots of business SQL code. And what this does is it just combines the different meters throughout the tables, and it just comes up with like, what's the source? And the source is, you'll see it in a little bit, it's like ties and trunks, and it's the major distribution parts coming into the network. So once we have that, then we start to compute our pairwise meter distance computations. So this is a super resource intensive task, and it's really computationally intensive as well. So what we use are Pandas UDFs to process this. And we also use, you'll see this in quite a few of our examples. We use this in just about every technique. We use combinations of SQL queries, the apply in Pandas and Pandas UDFs. We persist on we use the persist method on the data frames, and we also use lots of temporary views. And the reason we do that is it may not be the most efficient way to make this happen, but it is the most understandable way, because we're data scientists. We have strong SQL skills, strong Python skills. And what's great about Databricks is it gives us the ability to use what we're comfortable in and to make that all kind of a seamless high performance environment. And so when we compute these distances, what we do is we divide them up into manageable chunks so that we can then apply them and have that task run across the different workers in the cluster. So here we do that with SQL. And what this is doing is it's using the cross join to get the Cartesian product of the meters. So we get all combinations of that grouped by the source node and slice. And so here we're doing it because it's symmetric distances. We have that computation with this statement. And then we also, then up here, we use this monotonically increasing ID and the mod statement to give it a slice assignment. And so you'll see down here, this is what the source nodes look like, and then this is the slice number. So this gives us about 500 of these computations per batch. And these batches are then spread out throughout the cluster and assigned to the worker nodes. So here's how we use this. And it's actually applied in the apply in pandas piece, and it's right after the group by down here. So I'll show you that first and then come back up. So here we use that SQL that I showed you just a second ago, and then we apply a group by on top of that by the source node and the slice, and then we apply in pandas. And so each task gets assigned one of those slices to process, and that gets sent to this compute distance method here. So this function takes in that assignment as a pandas data frame, and then it applies the function, and this is from network X, and it actually computes the shortest path between those two meters. And so that gives us the resulting data frame that comes back out of that as the source node, the source target, and the distance that's going to be, that exists between those two. So once we have that, the rest of this demonstration I'm just going to do with 10 meters. So that's with 10 sources. So that's what this looks like here. You just see that processing actually took about 45 seconds. And one of the things we consistently do is we apply persist on the end like this. And this lets Databricks manage that cache on its own. And it will invalidate it if it needs to, but it makes this super easy so that this computation is only done one time. And then we get to use that speed boost anytime we access this temporary view. So here's some more on the cluster performance considerations. And what we found out is that computing that distance matrix was actually the most resource intensive task that we had. So the network X's get shortest path function is called n squared minus n over 2 times when where n is the number of poor reliability meters that you're working on. And so when computed using Python loops, the first time we tried this, it took over 10 hours, and we just gave up on that and decided that it's time to redo this using Pandas UDF. So almost immediately we went with that technique. And it turns out that DBSCAN is super fast for actually getting this done. And we use DBSCAN because it is primarily a distance clustering technique, how far away these are from each other. And so it was a natural fit. And you also didn't have to select how many clusters for it to produce. It automatically selects that on its own. So it seemed like the best algorithm for this situation. So what we do is we use SQL to actually craft that distance matrix, the result of that, and it returns it in a way so that it can quickly be turned into a NumPy array. And we use masking to make that happen. So this top part here, all it's doing is taking that view that we had created before and returning it and sorting it in a way so that it naturally aligns with NumPy. And so here you see we're creating that triangular matrix, that mask, and then filling it with zeros, and then using that mask to just apply those distances that we came back with. And so when we take this matrix and we take its transpose and add it together, we get the full distance matrix. And as you can see, this is the biggest one that we have in this batch of 10, and it's 646 by 646. So that's a fairly large distance matrix to compute, and it takes just over 3.5 seconds for that to complete. So this this is the main way that we achieve performance. And then we decided to just sequentially move through those different source nodes, and process those all individually. So that's what this looks like right here. This is the DBSCAN clustering method. And so we're basically just iterating over that list again. And then we compute and get those distance matrices. And then we apply DBSCAN to that. And we don't want to take a look at hotspots that are less than 10 meters so that we can be efficient in what we're applying our remediation to. And so here you see it just keeps track of that and builds that up as our hotspots. And it processed all 10 of these. And here you can see that one, that TI 810 that we were looking at before. It had 208,000, just over that number of computations that it had to do to get those distance matrix put together. And considering all of these together, it finished the entire task in about 23 seconds. And what we found is when we run this entire thing on the full set of data, it finishes in about 45 minutes. So in less than an hour, we're able to do all of this computation and identify which meters are actually fall into these hotspots. So here, this last command, this one kind of shows the results of the hotspots and kind of graphically lays that out for us here. So what you'll see is that this is the number of meters, the length of the bar, so size is the number of meters inside of a hotspot. So you can see that this is 132 meters for this one, and that's hotspot 5, and it appears quite often. It has hotspot 7 with 91, and you'll see it shows up quite a few other times over here. So that large one had quite a few groupings of hotspots of things that need to be remediated. So now I'll flip back over and I'll just show you an example of what that looks like to this one, to example. So here's what the results actually look like when you start to take a look at that. So we zoomed out, and what we want to do is protect DTE customers' privacy. So we're not zooming in too close, and we're giving you a view so you can get the feel for what this is doing without violating their privacy. So here, the different colors that you see represent the hotspots that they were assigned to. And with that blue one on the bottom there, you can see that it's not hard to imagine that those are actually following the power lines. And all of those dots represent meters that we identified as unusually poor reliability. And they've been assigned to a hotspot, grouping them because of their distances from each other. So probably if we can come up with a remediation and identify what the source and cause is for this and identify the right remediation that we can take, it should help improve power for all of these customers at once. And so at the bottom, what you see is an example of how we aggregate that information. So once these hotspots are identified, we take a look at all of the outage management system information, and we combine that together to show us like what were the top causes. Was it trees? What type of equipment was it that was failing? And take a look and start to give as much information as possible about these hotspots. And the actual dashboard shows much, much more information than just this, that you can go, you can hover over it and dig into all that detail about it. But what this does is it gives the engineers what they need in order to make decisions on that. And you'll notice that even though we have 2.6 million meters, the effect is what's happened is all of those normal meters have fallen away. And the only thing that's left are the really impactful areas that we called hotspots, where the engineers should be focusing their attention, because these are the ones that are experiencing the most poor reliability. So that's pretty much it. Please provide feedback to us. It's really important. And I just want to thank you so much for joining our session and listening to our solution. And I hope this helps you in your solutions as well.